Yo, what up, y'all? Welcome back. We are in the middle of studying the motion of a single pendulum. In this video, we're going to derive the ordinary differential equation that describes the motion of the pendulum. Don't worry about all that nonsense. The point of the matter is we're going to see if we can come up with an equation that models how the pendulum swings back and forth. When we say that we want a differential equation, what we mean is this equation is going to involve continuous functions and the derivatives of those functions. The unknown value in the equation is going to be a function. That's in contrast to algebraic equations where the unknown value is a scalar. So we're going to solve an equation. The solution is going to be a function over time that describes the behavior of our pendulum. Just like when writing algebraic equations, when deriving differential equations, it's not always clear what function is going to describe our motion. In our case, when we're looking at the dynamics of a single pendulum, we're going to make the claim that the desired motion is most easily modeled by this unknown function. I write it in red because it's unknown, which is theta of t. That's going to be the angle over time between what we call the equilibrium position highlighted in yellow. That's when the pendulum hangs freely with no velocity, no acceleration, no net force. In other words, it's static, hanging from our pivot. We say that if gravity is directly orthogonal to the support frame, that equilibrium position is where the bob comes to rest with zero potential energy. Another way to say that is it's 90 degrees perpendicular to the ground, or it's completely vertical in the frame of reference of the support structure. When measuring our function theta of t, we're going to start at that equilibrium position and actually measure the angle between that equilibrium, that vertical position, and the chord at any time t, where the bob is moving back and forth hanging from that chord. In this case, that chord has length L. So we're going to say that positive theta happens in the right direction. If I start at equilibrium and I go this way, I have positive theta. If I start at equilibrium and I go to the left, I have negative theta. The measurement of the angle literally is that angle between the yellow equilibrium and the orange chord. It may not be immediately clear why that function, because you could imagine that function does change over time, right? As my bob goes up, the angle is going to go from 0 at equilibrium to something like non-zero. It's going to swing back, get closer and closer, closer to 0, and then it's going to go negative, 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 closer, closer, closer to 0. Why would we focus on the theta rather than of the position of the bob? But here's a claim. If I can get this function, if I can get the function theta of t that accurately gives the exact angle at any time t over the motion of this bob, and I know the length of the pendulum chord has length L, and I can impose a frame of reference on the structure, then I could actually tell you the exact location of that bob, because the fact that the chord has fixed length means that this path is actually going to be an arc-shaped curve. It's going to be a portion of a circle. We talked about that last time. If you were to just rotate the bob 360 degrees, it would be a perfect circle. If we limit that rotation to a small subset of motion, that literally is going to trace like a semi-portion of the circle, or an arc. And what that means is if I know the angle, I can multiply that angle by the radius, and that would give me the arc. And then if I know this position, I could actually predict exactly where that bob's going to be by actually coming up with a function for arc length. We'll talk about that later, but the point of the matter is, when studying the pendulum, we're going to claim that if I can solve for this angle theta, I actually can predict the exact location of the bob at any time t during my observation of motion. With that said, the goal of this video is to derive a differential equation in terms of that function theta that describes that function completely. Here's a claim. Any function that predicts that angle over time for this pendulum is going to satisfy this differential equation. The second derivative of that theta plus g divided by L times the sine of that theta is going to be 0. When you see those two dots, that's called dot notation, and specifically double dot notation. it represents a second derivative. We'll break that down in just a second, but let's continue analyzing this equation. When you see g divided by L, g is the acceleration constant due to gravity. Usually it's 9.8 meters per second. And then L is a measurement of the length of the cord of the pendulum, which is the distance from the pivot position all the way to the point mass called the bob. Theta is unknown and desired, so in this situation, we're trying to solve for theta, where when I take the second derivative, add g over L times the sine of that theta equal to 0, what type of functions satisfy that behavior? Let me write this in a different way. Remember, we called this the double dot notation. What that means in notation from calculus is if I take the second derivative of my unknown and desired function theta, add it to g over L times the sine of that function theta, I will get 0. Now, I don't want you to believe me. The point of this video is actually to derive this from first principles, specifically starting with Newton's second law. I want to call out some special features of this differential equation because these are kind of famous in the study of differential equations. You would see this really heavily in an ordinary differential equation class. This term, the first term where we have the second derivative, that's called a second order term because I'm taking a second order derivative of my unknown function. Here, this is a nonlinear term because when I'm taking the function, I'm doing something to it and I'm doing a nonlinear transformation. Sine is not linear. Up here, this differential equation is written in terms of the function theta of t. In other words, we're trying to solve for this function, find functions that satisfy this relationship. That function is a single variable function that goes from some domain in the real numbers to some real number. In other words, it measures the radians between the equilibrium and the chord. Input is time, so that's real numbers. Output is radians, so that's some real numbers. When we have a differential equation where the input is a single variable, we call that an ordinary differential equation. If, on the other hand, we had a differential equation where we had multivariables in the input, we would call that a partial differential equation. When we see those things together, this is a second order, nonlinear, ordinary differential equation that describes the motion of the pendulum. The unknown and desired term in this differential equation is a function theta of t that describes this motion. In other words, if we were looking at this equation and we could somehow, instead of having a red unknown and desired function, produce a blue known function, perhaps maybe even in terms of elementary functions like, I don't know, sine or cosine or e to the x or log or something. I don't know what function is going to satisfy this, but if we could produce such a function that satisfies this equation, the claim is that that function would give us insight precisely. We could actually measure it, the exact angle between equilibrium and the chord at any time t, and the moment that we had that, we could predict the exact location of the bob at any time. So the goal of this equation is to solve it for such a function. If we're lucky, perhaps we could do that in terms of elementary functions. We're not going to talk a lot in this video about how to solve that thing. We'll leave that to a future discussion. What we're going to do in this video is figure out where the heck does this equation come from. So starting from first principles, just looking at the pendulum itself, can we find ways to generate this differential equation and verify for ourselves that this thing actually models the behavior that we're looking at? As a friendly reminder, this differential equation is a second order, nonlinear, ordinary differential equation. It has a second order term. It has a nonlinear function of the desired function, and then the function that we're looking for is a single variable function. This differential equation, the second derivative of our angle theta plus g divided by L times the sine of that theta is equal to 0. That describes the angle in the single pendulum and thus the motion. If the goal is to start from first principles to model this motion using the angle, like many famous derivations for known differential equations, we're going to start with Newton's second law. Remember, Newton's second law states that the sum of all forces acting on a point mass is equal to the constant mass measured in kg times the acceleration of that mass measured in meters per second square, and the sum of all forces, each force is going to be written as a vector with magnitude and direction, and the units of those vectors are newtons. Well, remember that a newton is kg times meter per second squared. The units actually work out in this. Let me repeat that in a different way. I'm going to claim that this equation is actually this equation in disguise. Somehow we're going to be able to translate the idea that force equals mass times acceleration. The net force on an object is the mass of that object times the acceleration of that object. Somehow we're going to have to translate this equation for the dynamics of this pendulum into this statement. That's the goal. Use this as a first principle and get that out. While working towards that goal, we're going to simplify our work by looking at each term in this Newton's second law equation separately. Let's start by looking at the left-hand side first. So we're going to say, what are all the forces acting on this point mass? If we're going to sum all the forces, we should probably understand what those forces are. And to do that, we're going to take a snapshot of our system in time. So right here, we kind of see this. Let's zoom in on this snapshot and think about what the forces are acting on that pendulum. Formally speaking, we made some really interesting assumptions, which is that there were no energy loss or air resistance in this system. The only forces acting on this particular point mass are gravity, which pulls directly down in the vertical position. In other words, if we're thinking about this as a vector, the direction of that vector is parallel to the line defined by the equilibrium position. And then we have this tension force that goes directly along the chord and kind of keeps that bob in that constant radius semicircle motion. The whole point of this is that the distance between the pivot and the bob never changes. And the way that that happens is as gravity pulls down, this tension force goes directly along that chord and makes sure that that bob never drops off of that semicircle arc. Another way to say that is when we're looking at the sum of the forces, if each force is represented as a vector from the physics perspective, not from the linear algebra perspective, but literally like a direction and magnitude, there are only two vectors, only two forces in this calculation. The tension force of the chord and the force of gravity pointed directly downwards on that bob. That means we could write the sum of all forces as the orange vector f of t in the direction of the chord plus the black vector f sub g directly vertically down. In mathematical notation, we're going to think about the sum of all forces. The net force acting on the bob is going to be the vector f sub t, which is the force of tension in the chord, plus the vector f sub g. Because the pendulum apparatus exists in 3 space, we would imagine that each of those vectors is going to have 3 components. However, one of the genius parts of this derivation is we're not going to worry about filling out the individual components. We're going to think critically about the behavior of those vectors in terms of magnitude and direction, and then try to correlate that with the idea of acceleration in our point mass. All right, when we're focusing on the net force acting on the bob, we see that there are only 2 forces. There's the tension force and the gravity force. We're modeling each of those as a vector in R3, and we're thinking to ourselves like, okay, each vector has magnitude and direction. We're going to avoid thinking about component form definitions, but we actually can say something intelligent about magnitude. If we look at the force of gravity directly down, pointing parallel to the line defined by the equilibrium position, we could say that the magnitude of the force of gravity is going to be the mass times the acceleration of gravity. In mathematical terms, what we're saying is that the 2 norm of that vector is going to be the constant m times the constant g. What's really nice about this force of gravity in terms of the direction, because it's naturally vertical, it fits in very nicely with a predefined frame of reference, an axis, an x and y axis, that align very nicely with the ruler placed under our pendulum motion. In other words, when I think about the x and z axis, if I say that this is an x-axis and then this is a z-axis, the force of gravity acting directly down can be naturally expressed in that frame of reference. This is in stark contrast to the tension force along that chord, because that tension force is not so beautiful when it comes from the frame of reference defined by the horizontal x-axis and then the vertical z-axis. With that in mind, instead of assuming that the frame of reference, that the measurement system that we're going to use has to be along the ruler and the equilibrium position, imagine that at any time t, we drew this axis horizontally through the bob that was literally tangent to the arc traced out by that bob in motion. So we're drawing this horizontal axis that literally touches that circular arc only where the bob is. And then we're drawing a vertical axis that goes from the pivot point through the bob off into space, so that now we have a orthogonal axis where the vertical component of the tension force is along that motion. The moment that we do that, the moment that we draw this blue horizontal axis and this red axis to understand what's happening with our tension force, notice that there's this kind of conflict. The force of gravity is most naturally described with respect to vertical and then orthogonal horizontal, whereas the force of tension is most naturally defined along the chord and then orthogonal tangential to the path here. The question is, can we figure out a way to express both forces in the same frame of reference? This is where our understanding of geometry comes into play. Notice here that we could actually decompose, we could do an orthogonal decomposition. We could take the force of gravity and state it in terms of the axis tangent to the arc-shaped path and the axis in the direction of the chord. Let me say that in a different way using visuals. The whole idea here is we want to understand the sum of all forces. We only have two forces. We have the tension force and the force of gravity. They are most naturally described in different frames of reference, but we can rectify that by decomposing our force of gravity along the frame of reference for the tension force. So specifically, when I'm thinking about my black gravity force, I can actually decompose that into two orthogonal vectors. I can decompose that into the force of gravity along the axis defined by the chord, along the direction that the tension force is, and I could decompose it as a separate vector as well along the axis tangent to my arc-shaped path. So in other words, when I add the red to the blue, I get the black. So if I go along the blue, then I go along the red, I get to the tip of the black. When I did that, I could then think, okay, well, when I'm looking at the tension force and then the orthogonal decomposition of the force of gravity in terms of the force of gravity along the axis defined by the chord, and then the component of the force of gravity perpendicular to that axis, what is now the sum of those forces? While visual representations are super powerful, it is also really important to be able to state this using a verbal description. So let's say this verbally. When we're thinking about the force of gravity, the black force acting on our pendulum bob, we can decompose that force into two separate components that are orthogonal to each other. The red force, which I call F sub G sub T, I'm going to call the component of the force of gravity in the direction of the axis of the tension force, in the direction of the chord. The orthogonal force, the other component of the force of gravity, the blue force, which I'm going to call F sub G sub T perp. That upside down T represents perpendicular. Mathematicians literally call that perp. P-E-R-P, perp. That's going to be the component of the force of gravity perpendicular to the axis of the tension force. So if I think about the red force along the chord, this is going to be the component of the force of gravity perpendicular to that. That's exactly what we saw in this visual. I had the perpendicular part of that and the one along the chord. These two forces combined give my original force of gravity. This orthogonal decomposition of the force of gravity into the frame of reference that is natural for our chord tension actually has some nice features. First, these two vectors are orthogonal. The angle between them is 90. They are literally perpendicular to each other. We write that in mathematical terms using that upside down T. The component of the force of gravity along the axis defined by the chord is perpendicular to the component of the force of gravity that is along the tangent line to the arc-shaped path of the pendulum. Moreover, we've assumed that this chord is inextensible, that the distance from the pivot point to the bob never changes. And what that means is if I look at the acceleration of that mass along that vertical axis, that bob will never go down or up. It is always going to stay in the same position along that vertical axis. It does travel instantaneously along the horizontal axis, never along the vertical axis. But Newton has something very interesting to say about that. We say that the net force is equal to the mass times the acceleration in any frame of reference that we do there. But that means when I'm looking at the difference, the net force between the force of tension and the component of gravity along that axis, those two forces have combined give zero net force. There is no change in acceleration along that axis. In other words, the net force between the component of the force of gravity along the axis defined by the curve and the tension force is zero. They cancel each other out. But this is really powerful because our whole goal is to understand the net forces acting on the system. We said there are only two of them, the force of tension and the force of gravity. We orthogonally decomposed the force of gravity into two separate forces. One of them was in the same direction as the force of tension, and the other was orthogonal to that. But we've just argued that these two forces cancel out, which means that the net force in this frame of reference is completely determined by the component of the force of gravity along the tangential axis to the arc-shaped curve. Specifically, we can actually animate what's happening. So in this animation, you're going to see here's the bob. I'm going to represent the chord as a dotted black line. That's what you see here. And then the tension force is in orange. The force of gravity in the direct vertically down position is in black. The component of the force of gravity along the axis defined by the chord is in red. And then the orthogonal component along the axis tangent to the path traced by the pendulum bob is in blue. What we're saying when we look at this is as this bob moves back and forth and back and forth, this black bob will never go off that path. That's the assumption that the arc length is constant. Thus, these two forces, the red and the orange force, don't have any net effect. That thing is going to stay constant along that vertical axis. In other words, the motion of this pendulum is completely determined by that blue force. So when that pendulum is moving downwards, the blue force, the tangential component of the force of gravity, is the thing that pulls it towards equilibrium. As it goes through equilibrium, that tangential component pulls it back. That's why the thing doesn't keep going off into infinity. The fact that the force of gravity decomposes backward is kind of pulling that pendulum back towards equilibrium. And notice that that horizontal component of the force of gravity always points back towards equilibrium. This is one of the nice things about a harmonic oscillator. It moves back and forth, and those two vertical components cancel out. Let's watch this decomposition in action very slowly. So as the pendulum moves, we see it moves away from its initial position. That upward force of tension is pulling that mass back up towards the pivot. The downward force of gravity pulls directly vertical. When we decompose that, we see, hey, that component in that direction defined by the axis of the chord cancels out the tension force. That bob doesn't move towards the pivot or away from the pivot. It literally stays at constant length. And then the force of gravity in the tangential axis is the real force acting to bring that thing towards equilibrium. Now, because it has momentum, it actually moves past equilibrium. The force of gravity stays constant both in magnitude and direction. The direction never changes. It always goes down. But with reference to the angle theta, that direction is actually decomposed, and then as it gets up to the apex on the left-hand side, to the most extreme point, that force of gravity in the tangential axis is actually pulling that pendulum back towards equilibrium. And in fact, we have a maximum magnitude when it gets up to that extreme point. So here we're seeing that vertical pull back, right? The horizontal force of gravity, that component here, is pulling back this way. the pendulum starts to react to that. It has acceleration because we're saying that the net force acting on a pendulum is the mass times the acceleration. We see acceleration along that path. As we get back down towards equilibrium, the magnitude of that horizontal component gets to zero. And that's because when we're resolving this, the vertical component of gravity is identical to the actual force of gravity. There's no horizontal component. And then we get back up towards that right extreme point, which is here. And we see that that horizontal component is back. And that's what happens. It just goes on infinity. Because there's no friction, because there's no energy loss, literally this thing just goes back and forth. This animation that you're seeing there is actually the dynamic representation of this mathematical fact, that we can decompose those force of gravity into two orthogonal components. These two things cancel out, and the force that's really affecting that motion of the pendulum is the force along that tangential axis to that arc. Because we've just shown that the net force acting on our object is actually fully contained in the force along that tangential axis, the next question that we ask ourselves is, well, what do we know about the force in that tangential axis? We actually have a lot of information about that force, both in terms of its direction and in terms of its magnitude. Specifically, when we think about the angle theta of t, we said that angle was positive as our bob moved to the right, and it measured the angle between the yellow equilibrium position and the orange chord. As that bob moves, the axis along the chord would be a straight line. But remember, if I move theta radians in this direction, the force of gravity is going to stay vertical, meaning that it's theta radians in the opposite direction. But this means if we zoom in on just where the bob is, the orthogonal decomposition of our force of gravity into two perpendicular vectors, these two perpendicular vectors actually form a triangle. Moreover, the angle between the red component of the force of gravity along the axis defined by the chord and the black force of gravity along the vertical axis is going to be negative theta, the opposite of the angle inscribed from the original pendulum bob and equilibrium position. We know by a famous proposition in trigonometry that for this right triangle, the sine of this angle is going to be the length of the opposite leg of that triangle divided by the length of the hypotenuse of that triangle. We can write that mathematically. The sine of this angle between the force of gravity and its vertical component along the axis defined by the chord is going to be the length of the side opposite, in other words, the length of the component of gravity in the tangential axis, divided by the length of the hypotenuse. We have to be a little bit careful. Both of these magnitudes are going to be non-negative. Sine could be negative, so of course this has to have an absolute value sign. But this representation actually tells us that we know the magnitude of the horizontal component of gravity along the tangential axis. If we bring this magnitude over to the other side, we know that's going to be the magnitude of the force of gravity times the sine of that angle. We already know what the magnitude of the force of gravity is. It's the mass times the acceleration due to gravity, but we know that each force has not only a magnitude, which we've quantified here, this is a non-negative number, it also has a direction. And the question that we might ask is, how do we assign a direction to the component of the gravitational force along that tangential axis? To get an answer to this question, remember the whole context that we're working in. We're trying to see the net force is equal to the mass times the acceleration. We've just got a very sophisticated look at what the net forces look like. We want to figure out how to impose a reference direction for forces, but to do that, that reference direction is directly related to the way that we measure acceleration in our system. In other words, let's take a look at the acceleration term in Newton's second law and see if we can get some insights using our investigation. When we say that the net force acting on an object is equal to mass times acceleration, the acceleration we're thinking about as a function in terms of time. Usually in our perspective in calculus, when we were thinking about acceleration, that means that we could take the second derivative of some other function, the position function, displacement function, something in terms of time, take two derivatives of that, and get the acceleration back. The question for this system is, what function are we going to differentiate twice in order to get our desired acceleration in Newton's second law? We're not looking for some random acceleration function. We're looking for an acceleration function directly related to the measured force along our tangential axis. In other words, we want information that exists in that frame of reference along that axis tangent to the arc-shaped curve. Moreover, when we're thinking about how that bob behaves, it actually inscribes that perfect arc based on the angle theta. We've said that the function theta of t describes the angle between equilibrium position in the chord at any time t, and that the positive reference direction in theta aligns with the positive reference direction of the ruler moving that way. So when the bob moves to the right, we have positive thetas. When the bob moves to the left, those values are assigned a negative sign. What's nice about that is that we can combine the angle theta with the length of our chord, and we can actually measure the length of the arc inscribed from equilibrium to the current position. That's called arc length. So it's as if we're taking a measurement of that curve in three-dimensional space, thinking about a one-dimensional object and asking ourselves, how long is that object? But we have a famous function to describe that. It's called the arc length of the segment between equilibrium and the position of the bob at time t, and that arc length is L times theta of t. Another way to say this is, if I allowed my theta to go all the way around 2 pi, we know that the circumference of the circle is going to be 2 pi times the radius. If I only take the slice of that circle, the sub portion of the entire circumference, the arc length inscribed by that particular portion, is going to be L times the number of radians that I traveled in that small slice. But if I'm thinking about this arc as a one-dimensional curve in R3, that arc is going to be changing along the tangential axis. In other words, if I were to cut that bob out as it's moving, the bob would fly straight along the tangent line in the axis that we're measuring that force. This suggests that in our hunt to describe the net force acting on our bob as the mass times the acceleration, if we think about acceleration as a second derivative, we could use arc length as the function that we differentiate in this relationship. Let's go ahead and do that. If we think about the acceleration as the second derivative of the arc length, or s double dot, because each dot represents one derivative operator, then the acceleration is the derivative of arc length, or the derivative of s dot. But s dot, the derivative of the arc length function, is the derivative of L times theta. That's the definition of arc length. We know L is a measured constant. This is a differentiation operator with respect to t. The constant comes out. That's the constant multiple rule, aka derivative operators are linear. When I take the derivative of theta, that's theta dot. So now I know s dot is L times theta dot. The acceleration was going to be the derivative of s dot, but we know that s dot is L times theta dot. So acceleration, we can bring the L out. That's the constant multiple rule. That's going to be the derivative of theta dot, or the derivative of theta, which is the second derivative of theta. So the measured acceleration in Newton's second law is L times the second derivative of my theta function. But what we've done in this situation is describe the net force as the force in the tangential axis equals to m times the acceleration. The acceleration was L times theta double dot. And these two quantities are in the same frame of reference. They're in the same tangential axis. Remember that we said we knew something about the magnitude of this force. We said it was m times g times the absolute value, but we hadn't assigned a direction yet in that axis. However, when we look at our visual, remember that the arc length is positive while the bob is moving to the right. This force actually causes negative acceleration on that arc length. In other words, as the arc length goes in positive, the force acts to counteract. It's in the opposite direction, which means not only do we have a magnitude, but we also have a direction in that tangential axis. We can bring the negative out because that negative is the opposite of the acceleration from my arc length function. So the component of the force of gravity in the tangential axis is negative m times g times sine of theta. Now I have two different expressions for the exact same quantity. I can now equate these two separate expressions. And that's what we do here. Newton's second law says the net force acting on a point mass is the mass times the acceleration. On the left-hand side, I know that that net force is going to be the component of gravity along the tangential axis with a direction assigned. That's the direction opposite to the acceleration experience of my arc length function. On the right-hand side, when I'm thinking about mass times acceleration, that's mass times the second derivative of the arc length function, which is m times L times the second derivative of theta. The left and right-hand side of this equation both have m. M is a mass, which we assume is non-zero. We can cancel those out or divide both sides by it. Not only that, but we can divide both sides by L, which leaves negative g divided by L times the sine of theta is equal to the second derivative of theta of t. If we bring this entire term over to the right-hand side, this is the second order nonlinear ordinary differential equation for the motion of my pendulum in terms of my function theta of t. The second derivative of theta of t plus g divided by L times the sine of theta of t is equal to 0. In this equation, we know g is the acceleration due to gravity. We know L is the measured length of the pendulum cord. And crazy thing about this is it is independent of our mass m. For good form, I do want to mention the last constant that we haven't talked about in the net force is equal to the mass times acceleration, Newton's second law. We assume here that the mass is constant. We assume that the bob is not losing mass over time. It's not like a rocket ship that's burning fuel. This is a point mass, all of whose value is located as a single point. It is a constant value. So that's literally a constant, a mathematical constant that we use throughout this whole calculation. The other thing that's interesting is that this mass is assumed to have no physical space. It exists in a point in space, no other mass distributed around that point. That gets interesting when we do our actual physical experiments with pendulums because in real life, masses actually take up space. The reason that that assumption is really nice is that we can think about the forces as acting on that single point, which means when we do our net force calculations, we can actually focus on that point in space. This is a simplifying assumption, but it's worth mentioning just to be clear. That's it, y'all. We formally accomplished our goal. We derived from first principles the second order, nonlinear, ordinary differential equation that describes the motion of our pendulum in terms of the function theta, which is the angle between equilibrium and the cord at any time t. The second derivative of theta of t plus g divided by L sine of theta of t is equal to 0. This equation came from Newton's second law, which is the sum of all forces acting on our point mass is the mass times the acceleration of that. Decomposing those forces in terms of the proper axes, and then thinking critically about how to align the force representations that we're looking with the proper acceleration function. In the next video, we'll start our discussion about solutions to this equation and talk about a very, very famous technique called linearization. Linearizing, turning a nonlinear into a linear by looking locally around a specific point. This is a famous way to bring linear algebra into nonlinear analysis. I'll see you in the next video.